This is a short talk I did at CVPR, and I'm doing it here with you all today, an expanded version of it. So happy to bring a little bit of CVPR to you. So we're Dan and I both work at Voxel 51. Our mission is to make visual AI reality, and we do that by focusing on helping you build better quality data sets and data-centric workflows. I am Harpreet Sahota. Got a master's in stats and math. I used to be a actuary, was a biostatistician, then a data scientist. I've been kind of doing code plus math for 12, 13 years now. I used to work at Deci, Pachyderm, and Comet. That's where I've kind of got my, those three roles were kind of my intro into developer relations and where I am now, my current role as hacker in residence at Voxel 51. Feel free to follow me on LinkedIn or follow me on Twitter if you'd like as well. That's at Data Science Harp. More active on Twitter, and you get more insight into me as a person, if that is what you are interested in. Feel free to follow us, Vox51, start that GitHub repo. If you don't mind, follow us on LinkedIn to stay connected with all the content Dan and I push out and the stuff the awesome team does. And go ahead and feel free to try 51. That being said, we're going to have a little bit of group participation, right? I want you guys to drop in the chat how you would group these, right? Take a look at these foods. What is the first thing that comes to mind when you think about how to group them? So go ahead and think about that. We got egg rolls, we got empanadas, we got samosas, right? We got some people saying shape. Yep. Some people saying shape and then geography, right? Fried food, great, great texture, awesome, right? Color, yeah, definitely, right? So we can definitely group them based on shape, right? Empanadas got that half moon shape, egg rolls got the kind of oblong shape, and then samosas are triangular, right? We can group them by geography, right? Egg rolls come from Asia, empanadas from Latin America. There's so many different ways that we can group them, and it's easy for us to think about these similarities, right? And it's easy for us to recognize that these are all savory pastries, deep fried and enjoyed in different parts of the world. But you know, we can figure out how to group them. It's easy for us, right? Like I mentioned, shape, country of origin, flavor profile. But how would a machine group these? How would you get a machine to do this, right? How can we teach a essentially robot to group these? And the answer to that is embeddings. So what is embedding? So in embeddings you can think of them as distilled knowledge, right? They're just compact, meaningful representations of data. What an embedding does is that it takes this high dimensional data, like image or text, and then transforms it into a lower dimensional form that captures the most important information. And this is really useful because it allows us to do some interesting things, as you'll see. But let me break this down a little bit. When we talk about embeddings, there's three kind of things that I want to point out. That's low dimensional, learned, and then meaningful relationships. So low dimensional, meaning that embeddings are mapping high dimensional data like words or images or graphs to this lower dimensional continuous vector space. And they're not arbitrary vectors. There aren't arbitrary coordinates either. They're learned from the data by the inherent structure and relationships within the data that they're trained on. And with these, we can find objects that have kind of similar coordinates in this system because they'll be more likely to share really important characteristics. And these similar points can be, again, mapped to nearby points in this embedding space, while dissimilar ones will be further apart. And this really enables machines to, machine learning models really to understand and leverage these underlying patterns and similarities in data. Embeddings come in all types of uh, uh, shapes and sizes. This is by all means is not an exhaustive list of the types of embeddings. But when we think about embeddings, we can typically think about them by modality, right? Text, image, graphs, audio, video, time series. But these embeddings all share a fundamental goal, and that's transforming complex, high-dimensional data into this compact, dense vector representation that's going to capture meaningful features and relationships within our data set. And this is going to make tasks like similarity comparison, classification, retrieval, and generation possible. And so when we're able to map raw data to this continuous vector space, uh, the embedding is what is bridging that gap between what is interpretable by humans and what can be processed by a machine. And what we're going to talk about specifically here over the next couple of slides is sentence and document embeddings, image embeddings, and then cross and multimodal embeddings. So real quick, sentence and document embeddings. You know, I think we're all kind of familiar. And if you're not familiar, my apologies for making the assumption, but a while back there was word to vec, for example, right? They captured word embeddings, and we saw that we could do interesting things with word embeddings, like embedding arithmetic, where we can take something like king minus man and get a resulting vector for queen, right? Something similar like that. And while word embeddings are powerful, they struggle, though, to capture the meaning of a longer text sequence. So sentence and document embeddings, they address this limitation by representing an entire phrase, sentence, or document as a fixed length vector. So it doesn't matter the number of tokens that are part of this chunk of text that you're going to embed, all of it gets mapped to this fixed length vector. And when we consider this entire text sequence, we're able to capture more high-level semantics and contextual relationship between words. And so we can encode the general meaning and kind of intent of that text. And this is really useful for doing similarity search, semantic search. For example, canonical kind of example is retrieving documents that are relevant to a query, right? That's the canonical kind of RAG example, or text clustering to discover some kind of structure and themes in a collection of documents. Image embeddings transform this high dimensional visual data into a dense, compact vector representation. So with these embeddings, of course, we can do the same thing, measure similarity in embedding space. And the clustering is typically based on visual features or visual similarities. And this allows embeddings to really power tasks like image retrieval, where you can find visually similar images. But these embeddings also capture features in a hierarchy of low to high features, low level to high level features. So low level features, what I mean by that, these are just like basic visual elements like edges, textures, colors, shapes. And this is the stuff that we traditionally associate with convolutional neural networks capturing and extracting these type of features kind of in the earlier layers. Then mid-level features are building on these low-level rephrase that, sorry. Mid-level features are building on these low-level features, and they're representing more complex patterns and local structures in the image. And we typically think of the middle layers of a CNN capturing this information. And when we say that an embedding is capturing semantic information, it doesn't mean that the model is understanding languages or words like the way a human does. It's just referring to the model's ability to encode this high-level, meaningful visual concept that is in that image. For example, image embeddings can capture a image's content and context, like the object, scenes, textures, and the relationships. So the visual semantics, when I say that, this is what allows the model to really kind of quote unquote understand what's in the image at this conceptual level. So again, semantics in the context of image embeddings again refers to the model's ability to encode this meaningful high-level visual concept, but not human language. And I know I mentioned, I said CNNs during this slide, but obviously we can also get these type of features from vision transformers and things like that. But again, I also mentioned that there's a limitation. They're not capturing language with these image embeddings. But for that, we have another type of embedding. That's cross and multimodal embeddings. So cross-modal embeddings, these just are super powerful, and they map data from different modalities like image, text, and audio into this shared vector space. So under the hood, a cross-modal embedding model is using a separate encoder for each modality, and it's going to map this raw data into this shared dense vector representation. These encoders are trained to optimize an objective that's going to align the vectors from the different modalities. A common approach to this is the contrastive loss, which is pulling the embeddings of corresponding image text pairs closer while pushing the unrelated pairs apart. Another type of loss is adversarial loss, where we have a discriminator that's trying to distinguish between modalities with an encoder trying to fool it. But by mapping these different modalities into a common space, we can use the vector representation from one modality, for example, a text query, to find the most similar or relevant vectors from another modality, for example, images. And this allows doing some interesting types of retrieval. So we can retrieve images using text or find relevant text given an image, or we can use audio to retrieve an image, as we'll see a little bit later. But two particular types of embedding models we want to talk about are clip and image bind. So clip was developed by OpenAI, and it generates embeddings for both images and text in this shared latent space. And this lets us do really cool tasks like zero-shot image classification, as well as cross-modal retrieval, or text to image retrieval. And what it does, it's jointly training an image encoder and a text encoder to predict the correct pairings of a batch of image and text pairs from the training examples. It's a simple but powerful architecture. We have a text encoder, which is going to be a 12-layer, 512 dimension transformer with 8 attention heads, and it's just 63.43 million parameters in total. We have the image encoder, and in the clip paper, they tested a bunch of different types of image encoders, but the canonical clip ended up using a vision transformer, and this is going to map images to a embedding space. And then there's the projection matrix, and so the projection matrix are essentially a series of learned linear transformations that are going to map the encoded image and the text features into the shared embedding space. And this is what allows us to compute similarity scores between images and text. So this projection matrix, it's kind of WI by WT. I by T matrix. And this is learned end to end along with the image encoders. So we train this using a contrastive loss function, and it's bringing the embeddings of the text image pairs closer if they're correct, and separating them or spreading them further apart if they're incorrect. So the contrastive objective, again, it pulls a projection of the matched image text pairs together, pushes the unmatched pairs apart. And so the model in this way is learning really meaningful aligned representations. So a couple of key steps here. Again, there's the contrastive pre-training. So the image and text encoders, again, are trained on a data set of 400 million image text pairs. Like I mentioned before, driving the point home, the contrastive loss brings embeddings of the matching text image pairs closer while pushing the non-matching pairs apart. And from this, we're able to do really cool things like zero-shot classification, where the clip model will generate a text embedding for the target data set's class label, such as a photo of a dog or photo of a car, et cetera, and get the matching image for that. And also, again, with the zero-shot prediction, clip is going to encode the image encoder and predict the class whose text embedding is most similar to that. And building on this is image bind. So image bind is actually learning a single embedding space that's binding 6 modalities together. That's image, text, audio, depth, thermal, and IMU, IMU being inertial measurement unit. And so the model is using, it's making an exploit of this, the natural co-occurrence of images with other modalities. And through this, we're learning a shared embedding space that's going to bind modalities together without actually requiring paired data for all the modalities. And a really clever trick they used for this was actually using a frozen text and image encoder from OpenClip as the foundation for this shared embedding space. And so then to align the other modalities, the audio, thermal, depth, IMU, into this shared embedding space, the embedding space from the text and image pairs of OpenClip, they use a modality-specific encoder that is trained to project the input into that same semantic space as the frozen OpenClip encoders. So only the new modalities encoders and projection layers are trained, but the clip image and text encoders are fixed. And so this alignment is done through contrastive loss, info and CE, that is going to, again, encourage the embeddings of paired modalities to be similar while pushing the embeddings of unpaired modalities apart. So it's an interesting strategy to use a frozen clip encoder because we're now able to leverage this strong image text representation that we get from clip to extend this to new modalities. And it's this really smart way to build upon existing models. And so with these embeddings now, we can do all these cool things that we're going to talk about right now in code. We can do similarity search. We can compare model representations. We can do semantic search, zero-shot prediction, cross-modal retrieval, as well as concept space traversal. Everything is on GitHub. I'll drop a link in just a second, but here is a QR code that will take you right to the GitHub. So I'm going to go ahead and pull up my code now. All right, let me drop a link here to the chat, to the GitHub, so you guys can get it. All right. Cool. So let's talk about all this in action. So I mentioned we can do 5 things with embeddings: similarity search, compare model representations, semantic search, zero-shot prediction, cross-modal retrieval, and concept space traversal. Right now, I'm going to talk about the first 2: similarity search and comparing model representation. So I'm doing all this with the open source library FiftyOne. Pip install FiftyOne, and you'll be able to do everything I'm doing here. There's no kind of hidden fees or anything associated with it. Just pip install it and you'll be good. And what I'm doing is I'm using the Stanford Cars dataset. We have an integration with the Hugging Face hub, so you can pull any dataset from Hugging Face as a FiftyOne dataset, which will allow you to interact with it using the SDK as well as the app. I'm just dropping some sample fields here that I don't need. Next, what I'm going to do is load models from our model zoo. So we've got a pretty robust model zoo that you can check out. I'll link to it here. I'm going to take a clip model, a Dino V2 model, and a DenseNet model. And then with these, I'm going to use the FiftyOne brain, which allows us to do some really interesting things. We can visualize our data set, index our data set, compute uniqueness, find possible label mistakes, and find hard samples. Click that link. You can learn more. I also will talk about this in the Getting Started workshop. But what we're going to do now is with just really one line of code, essentially, compute embeddings. Computing embeddings using clip, computing embeddings using Dino. Dino V2 is a bit slow to run on CPU. Took me over 20 minutes to run this locally on my M3. But Dino gives some really interesting and good representations. If you got a GPU, it'll go quicker. And then DenseNet embeddings. So I'm computing embeddings with just a single line of code. Next, what I'm doing is I'm taking those embeddings and I'm going to project them into a lower dimensional representation. That is a 2D representation using UMAP. And I'm going to do that for Clip, DenseNet, and Dino. And then what I'm going to do is compute a uniqueness score for each image in the dataset using just one line of code here, one function call, compute uniqueness using Clip, Dino, and DenseNet. And then I'm also going to create a similarity index, and the similarity index will allow us to do similarity search and semantic search and things like that. So we support a number of different backends: Lance, Milvus, MongoDB. I'm using Quadrant here because we're using Quadrant in all the other examples, not because there's anything special about them, but that's just what we're using. And now I'm going to show you what we could do. So all I did was FiftyOne app launch. It opens up in the browser. We have the Stanford Cars dataset. First thing I want to talk about is uniqueness. So here you can see that we've computed uniqueness for each of our images here. And you can see the uniqueness scales based on Clip, Dino, and DenseNet already are different, right? So we're able to see the model. The way our model is representing uniqueness is different. So we can open up any random image here, for example, this one, double click on that, and we can see the difference in uniqueness scores, which is interesting. That in itself is cool, but it'll be also cool if I just open up this embeddings panel. What I'm going to do now is let's just look at the clip embeddings. I'm going to color it by the uniqueness. And you can see that, we're able to kind of find some interesting pockets of cars. For example, like this little island of cars here, right? We can see what these look like. And we can see that, oh, they're all kind of, as vans, essentially. And now what we can do is you can select these individually if you want. You can use a shortcut, select them all, but I'm just going to select some here. And I'm actually going to change the embedding space that we're looking at. Now, instead of looking at it with the clip embeddings, I'm going to look at these images using the DenseNet embeddings, right? And we'll color by DenseNet uniqueness. And now you can see the way that the model is represented, these images is different, right? The embedding spaces that are created by these models are different. And again, we can look at the Dino representations as well and color by Dino uniqueness. And you can see the way that these are represented are a bit different, right? I really like Dino. I think it's a great model. Like the way it represents things are quite fascinating. So you can highlight these and you can see, for some reason this cluster is clustered together, and maybe because it's like the back of cars kind of facing in, or could be the angle or something, right? It's quite interesting to kind of see. So that allows us to do this comparison of uh, model representations. Another thing you could do with that, so we computed uniqueness. We can also look at similarity, right? So I can scroll down here and maybe find a car that I like. For example, I believe this is a Rolls Royce. One day I hope to have this. If FiftyOne goes public, that would be amazing. And what I could do is look at similar samples. Of course, I could look at similar samples using each one of the different indexes. Let's just look at the 5 most similar here. Let's just use the Dino similarity index to find the most similar ones, right? And you could see boom, 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 boom. You can see where these are lying in the embedding space. Interestingly enough, these are all actually Rolls Royces, so that's pretty cool how that was done. And so we can, of course, compute similarity in that way. Another way we can uh, compute similarity is actually through a text prompt. So what I'm going to do is let's just compute now. We're going to use Clip because Clip is the only one of the embedding models that I have here that support text image kind of retrieval. And I can maybe just find 10 of the most similar to this query. And maybe this query I want is like a high-end luxury vehicle, right? And apparently a minivan is a high-end luxury vehicle, right? Again, these are, just clip embeddings, clip representations. We can also say something like Japanese sedan and kind of see what pulls up, right? And we do, in fact, get some Japanese sedans. Point being, this is what embeddings allow us to do, right? So right now we've seen similarity search based strictly on visual kind of semantics. We've seen similarity search based on text to visual semantics. We're able to compare model representations as we've done here as well, which is really interesting for you to really understand your data, get a sense of what's in it and what's going on. Next, what I want to talk about is document search. So this is kind of like the canonical RAG use case here. So I've listed out all the steps you need to do here. We're making use of plugins heavily throughout this entire, presentation. The thing with FiftyOne is that it is completely open source, and there's plugins that are contributed by community members, by Dan, and soon by me. I'm the new guy on the block, but I'll be contributing plugins soon. But we got a plugin here that's going to allow us to do semantic document search. So create a data set that I've put on Hugging Face Hub here that you can take a look at. And I'm using this plugin. I've listed what you need to do here. And we can now just see it in action, right? So I'm going to look at the CVPR papers, right? And what I've done here, so just a little bit of backstory, right? CVPR was maybe just a few weeks ago. It feels like forever. And in honor of CVPR, I created this data set, and this data set was the about 2,400 of the 2,700 accepted papers, and an image of the first page of each one of these accepted papers, right? And so what I did was I used FiftyOne. I used the plugin for OCR and detected all the text blocks here. And then I took everything that was detected in the text blocks and then uh, extracted the text using OCR, embedded that text, pushed it to a quadrant vector database. And so now with that, we can do some semantic search. So we'll open up the plugins in FiftyOne, hit the backtick operator, and we can do semantic uh, search. And now I could just, do a search here, and, we can lower this down to maybe about 0.51. That's a good number. And maybe the query here, we can say something like embeddings for multimodal retrieval, right? And we can find all of the papers that match that and exactly where in those papers that it matches that. And again, this is using the clip model. Sorry, this is in this case using BGE, a small BGE model, right? With a better embedding model that's fine-tuned, you'll get better results, of course, but just to demonstrate what you can do here. And so that is the semantic search over documents. So that's the thing number 3 we can do with embeddings. Next, what I want to talk about is probably my favorite application, cross-modal retrieval. Right. So cross-modal retrieval. This is a really cool plugin, and with this, we're actually going to use image bind for this, and it's done via a plugin that one of our team members here, Jacob, had created. And it's essentially a plugin that's going to search for images similar to a given audio clip. We're going to use image bind. Image bind is going to create a shared 1024 dimensional space for images and audio. We're going to store all this into quadrant. We'll have a UI in FiftyOne that we're going to upload our audio to, and we'll find the similar images. This plugin supports OGG and WAV formats, but not MP3. And again, just to kind of, I put copious notes here for you guys, so feel free to read all this, but just to quickly talk about image bind, right? We're learning a joint embedding space across 6 modalities: image, text, audio, depth, thermal, and IMU. We don't need all the paired data combinations. We can just use images as an anchor to align the modalities. Each modality is going to have its own encoder. We're going to have a vision transformer for images, audio spectrograms, and depth maps. We're going to have a transformer for the IMU sequences. We'll then have a modality-specific linear projection that is going to map the encoder outputs to a shared space. In this case, the shared space is the open clip space. And then we'll use a contrastive loss, info, and CE during training. The other modalities are going to be learned to align with the clip embedding space. And that way we can connect the unpaired modalities, for example, text and audio, through this image-based kind of training and retrieval. So let's go ahead and pull this up here. In this case, I took a data set just to show you what I did. I'm using replicate here. So if you don't have a replicate API token, you don't need to do that. Downloading a data set from Hugging Face. In this case, it's an instruments data set. The instruments data set was sequential in the sense that it had all images of one instrument, then the next, so on and so forth. So I shuffled them up and just took 250 of them. And then set the operator timeout to just be an arbitrarily high number, just because it takes a while to embed everything, send it to replicate, and then there's that latency over network. And I hope we're not going to suffer any latency now. I did my best to warm up the space by on replicate, but let's see this in action. So I am sharing screen, and I'm sharing audio as well. And so what I'm going to do is I'm going to select some audio here. In this case, the audio I'm going to select is let's just select here a bag llama. In the bag llama, right? So it sounds like that. So let's open that up. Let's hit search, and you can see that with the sound, we're able to retrieve the appropriate images for that. We can, of course, clear that out. Let's try it again. Let's just show you this one. right? So this is a violin, and then we can search for that violin. You can see that with a audio clip, we're able to retrieve images of the instrument that created that sound. And this is done using image binds embeddings. Oh, something I forgot to show you actually with the Stanford Cars data set was actually a reverse image search. So I'm just going to show you that real quick uh, while I remember. Me and my son love to go to car shows every Sunday. You can catch us at a random car show. So these are the ones from the last week. Uh, I, for one, love classic cars, but we can pick a random car here. It's probably going to have to, nope, download. And we can find similar examples to that car that way as well. So there might not be any old school Impalas in the data set. We could try another one as well. Let's look for another car. In this case, maybe something less crazy, like a classic Mustang. Right. Just a limitation of the clip model, not necessarily the tool that we're using. Cool. So next, I need to show you concept space traversal. So let's show you this cool thing. So I've talked about concept space traversal here in great depth, but essentially what we're going to do is we're going to navigate and explore this high dimensional vector space where the data points are embedded using clip. We're going to try to manipulate semantic relationships that are captured by an embedding. We're, again, just going to use an embedding space that's just a high dimensional vector space where similar concepts can be closer together. We'll use some similarity measures. In this case, we're going to use cosine similarity. And then we're going to traverse this embedding space using some linear interpolation. So we'll create intermediate points between concepts, and then we'll use some weighted average of these vector representations. We'll do some vector arithmetic to take a starting image. We'll add a phrase to it and then kind of augment that vector using a word or phrase, and then do some nearest neighbor search. It'll probably be easier just to see it in action. So let's go ahead and pull that up. This is a data set that I will be putting up on Hugging Face soon. Color swap, there's a paper that came out. If you type in color swap paper, pretty cool paper. Definitely check it out. Color and word order data set for multimodal evaluation. So I parsed this into a 51 data set. Let's open up our concept traversal panel, right? Let's start with an initial image. I don't know. Let's take this image. Now let's make it scary. Then let's weight the scariness quite high. And let's add more kind of scale to that. And we'll find, oh, I didn't set the initial image. There we go. All right, so that was my bad. I need to set the initial image first. User error. All right, so again, here, let's just I'll select this, set that image. Let's make it so you can see here I've played around with this a little bit, but we can make it scary and then aggressive. How about that? Can add some scale to that. And so we're starting with this initial image. This initial image will be parsed. We'll get the embedding of this using clip, and then we're going to do some vector arithmetic and add some scariness and add some aggressiveness to this, and let's kind of see what ends up happening. So obviously limitation of the clip model and the data set, but maybe we can make this, even just have a mean. Add some meanness to it, make that meanness bigger, make that, there we go, and traverse that image space. And yeah. Doesn't pull up exactly what I hope to, because obviously I don't have that many images here. It's a limitation of the data set in the model. We could try another one actually. Let me just drive the point home, man. Gotta prove to you guys that this is doable. Let's go to let's see. Let's look at we can look at this, a snake, and maybe we can say more animated. and then cartoonish, and then we'll, all right, we can see we do kind of get something animated and cartoonish. But this is, concept space traversal. Of course, if you have a richer data set with more concepts, you might be able to do a lot more than that. And then finally, the last thing I want to show you is zero shot, zero shot prediction. In this case, zero shot detection. So let's do this. This is pretty interesting. Here's an image of uh, Darth Vader and Luke Skywalker, right? So I'm going to select this image, open up our plugins, and I'm going to do a zero shot detection. This will take a little bit of time because I'm running this on CPU, uh, but we can put here Vader, Darth Vader, and then we can put Luke Skywalker, right? We'll use just the selected sample and we'll hit execute. And this will take just a moment to run because, of course, oh, actually, it took quicker than I thought it would. So where is that picture that I had detection on? Looks like I broke my own FiftyOne thing somehow. Um, I accidentally put Control C. All right, I accidentally hit refresh, so I broke FiftyOne. My bad, y'all. I should not hit at that key. But the point I was trying to make is that you can actually use you can do zero shot detection with embeddings. Um, so we didn't see it happen. Trust me, it worked when I was doing it earlier, but it would actually do detections using the YOLO world model. So yeah, that's pretty much it. I know we are over by a lot, so I'm going to stop that and just answer some questions. Um, we'll get right to it. So I'll start from the top here. Um, So D. Dotton, your question was from a while ago. So along with depth and thermal, what other senses are you focusing on? So I talked about the 6 modalities of image bind. So depth, thermal, audio, IMU, text, and images. Um, Vithal is asking in text embeddings, we know the dimensions, which, unique words in a data set. How do we get dimensions in vision embeddings? So you're just projecting everything into a fixed length vector. So you can arbitrarily choose the dimension that you would like. So initially, like your image will have some resolution. Your resolutions can vary across your data set. But once that image is tokenized, you can then project it, into a fixed length vector and kind of bypass that kind of issue. Just a point though, like text embeddings, the you can have a vocabulary, but each word in that vocabulary itself is also mapped to an embedding vector of fixed length as well. So same kind of thing there. Um, that doesn't look like a question for me. If you're new in learning AI/ML but have a software QA background, can you get an entry-level AI/ML job? Yeah, I mean, definitely with a lot of work, with a lot of hustle, you probably can. But honestly, I think there's an emerging role now called AI ML kind of QA analyst, QA engineer, which I think you should look into. I saw Daliana Liu talking about that on LinkedIn. So how do you overcome the challenges in alignment with multiple modalities? Well, each modality will have a encoder specific to it. You do a series of linear projections and you project that onto whatever shared embedding space that you want to project that into. In the case of image bind, they projected it into the clip embedding space, but there's new work that is coming out, um, from Google and Meta, where they are actually just learning end to end. So true multimodality. They're learning a shared embedding space end to end. Neha will give a link to the GitHub repository. Are embeddings a regularization technique? Embeddings are not a regularization techniques, though embeddings are typically normalized through the process of training. Are there data embeddings too? Large spreadsheet type of, that's a good question. You can, of course, embed that. One hot encoding, I think, comes to mind. But yeah, you can embed any vector, really. Can embedding algorithms be trained to improve production performance? I don't know the answer to that, but hit me up and we'll see if I can get you the answer. Can embeddings be trained to improve model semantics? Yes, you can fine tune embeddings on your own data set. In general, when we have embeddings without knowing how the training was configured, how can we tell? Well, we talked about that a little bit when we're comparing model representations. So you can kind of look at it that way. In general, it's really going to be hard to understand anything that an embedding is capturing, without doing some type of visualization and kind of looking into it and kind of seeing what nearest neighbors look like, and maybe from there try to get some heuristics. But in general, I would not try to understand embedding vector. When you have more than two modalities, do we do pairwise clip loss or is there multimodal joint clip loss? Everything is kind of contrastively learned. So I don't know exactly the answer to that. Info NCE is one of the loss functions. I think you can extend that. But yeah, I don't know the answer to that off the top of my head. Sorry, Dan, unless you might have some insight there.
No, exactly right. It's
Yeah.
all about how you train it contrastively. It's all about whether you're pushing or pulling and how you do that. How the vectors will play out at the end is what's most important. Getting to that right vector space and encoding and decoders. I think the losses in between is more just on the choice of the model architect.
Awesome. All right. Well, thank you guys so much for joining. Hope you guys enjoyed it. If you got any questions, feel free to let us know. We've got a Slack community that you can join in as well. And we do a getting started workshop every month, getting started with 51. So if you want to learn how to use the open source tool I just showed you in more of a deep dive, definitely check that out or just look at our blog. We've got a ton of tutorials that will show you how to do all this cool stuff. Neha, thank you so much for joining us and for sticking around. Appreciate you being here. And thank you everybody for hanging around a little bit later. Cheers.